Hello again. This is just going to be our last video and also the last R session about the descriptive statistics. We are just going to learn a few R comments where we can use to collect descriptive statistics about a sample data. So first we are going to start by calculating some univariate descriptive statistics such as the sample mean, sample standard deviation, variance, and quantize. Then we are going to see how we can draw histograms, or for bivariate descriptive analysis, how we can draw scatter plots, etc. So let's start with our first application. So this R session is just going to follow the sample data in the Excel file named as RS10 descriptive statistics. Also, the same applications which we are going to perform in the R console are also available in the Excel as well. So you can check this Excel file. You can analyze this Excel file and you will realize that all of the applications that we are going to do in this video are also practiced here, but it is up to you to learn how they can be performed in Excel. I recommend to learn them both because, I mean, in many of the classes, industrial engineering classes, you are going to use Excel in any way. However, it is also a good idea to learn the main statistical functions in a programming language as well. So you need to have your both hands strong in that sense. Okay, so the first application is explained here. It says, use the built-in scan function to take the 27 observations from the first tab. So the first tab has a sample of 27 observations. So we have copied these values. Okay, so right click and you say copy. So we have copied these values, these 27 values. Then we move to the R console and we are going to store these in a vector that is called X. So we write scan function, scan. And when we press enter, it says, please write me down the first observation. Now, all you need to do at this point is to right click and paste everything. All of these values, which are separated by cells, will be written into a new index of this vector. And then it is going to ask you to enter the 28th entry, but there is not any more entry after the 27th entry. So you simply press enter at this point. Okay, press enter at this point, and it will say that I have read 27 items. Now your X vector is stored here. Now in the following applications here, it is just going to ask us to calculate the mean of the vector, sample mean, which can easily be calculated by this command, mean of X. You can calculate the median of this vector, which is 15. Now you can easily determine the median by sorting the sample from smallest to largest, and you can determine the median by yourself as well. But the median can also be determined by the command line median. And then we are going to produce quantiles. Okay, quantiles. So let's just say we are interested in 50% of quantile, 50% quantile. The 50% quantile is also the median. As you can see, 50% quantile is here. And we can also produce more than one quantile by writing down these percentages in the form of decimal ratios, of course. For example, I can collect 10%, 25%, 50%, 75%, and 90% quantiles at the same time in a single comment line. Okay, so this can produce me multiple quantiles. So if the quantile percentages are given in a vector, Okay, so let's just say I am interested in 10%, 20%, 30%, and 40% quantiles. Okay, so I'm just going to store these values in the percentage vector, and if I write quantile and then I write here the percentage vector, then I will get 10, 20, 30, and 40% quantiles of my sample data. All right, so another thing that we can calculate is the sample variance. So let's just say the mean of the sample is stored in the X bar vector, and we can also calculate the variance of the sample in S2 variable. And this is the sample mean, and this is the sample variance. And you can also calculate the sample standard deviation directly by using the SD comments. Okay, so SD here stands for standard deviation, and we can simply store it in S, and S is here. In fact, if you take the square root of the sample variance, you are also going to get the same value as well. All right, so one final thing that we can do at this point is to draw the histogram of the observations. Now you see this histogram gives an idea about the distribution of the parent population by looking at the sample behavior. However, with such a small sample size, such as 27, it is not a good idea to make any comment on the parent population distribution. However, for larger sample sizes, histogram is a good tool. It's a strong tool to put a hypothesis on the distribution of the parent population. Now, in the next practice, okay, so this is about a univariate analysis. We are going to analyze two variables on the same sample, observed on the same sample. In the question 4, we have 100 second-hand automobiles, and the first column shows the odometer values, while the second column shows the sale prices. In fact, you can see this in Q4A. So these are the odometer values of the second-hand automobiles in thousands of kilometers, and these are the prices in Turkish liras. However, these are very old prices. Now it is impossible to purchase an automobile with these prices. So what we are going to do is, I am just going to copy my first column. So I will copy my first column, and these are my X values. I am just going to write X scan and paste these values here. Okay, paste them here. And I have stored my odometer values in thousands of kilometers. Now I am just going to copy my second column, and I will say Y values scan and then press enter. Then I'm just going to paste my second vector. Now I have X values, the travel distances of the automobiles, the odometer values, and the second-hand prices in the second vector. So how am I supposed to discover the relationship between these two variables? A scatter plot is a good idea. A scatter plot is a good idea. So I will plot the X values in the horizontal axis, and I will plot the Y values in the vertical axis. So I will say plot XY. And you see, as the odometer values increase, the second-hand prices are decreasing. Okay, the second-hand prices are decreasing. So there seems to be a negative relationship between these two variables. And since our sample size is moderately good enough, because 100 observations is a moderately good size, it is a good idea to make this comment. Okay, it is not very dangerous to make this comment. We can say that for automobiles who has traveled between 20 and 50,000 kilometers, as the travel distance increases, the price decreases. Okay. Now, unfortunately, you cannot make any comment on the second-hand automobiles which have traveled more than 50,000 kilometers or less than 20,000 kilometers. You can only, by looking at the sample data, you can only make a comment about the parent population if the parent population, the automobiles in the parent population, have traveled between 20 and 50,000 kilometers. Okay, so you can make an interpolation between these values, but you cannot make an extrapolation. You cannot make any comment on an automobile which is not seem to be in this data, which is seem to be outside in this data. I mean, by looking at these plot diagrams, you cannot say for an automobile who has traveled 100,000 kilometers, the price is going to be even less. You cannot say. You can only make this comment for automobiles between who have traveled between 20,000 and 50,000 kilometers. Okay, so by looking at the plot diagram, we can make such a comment. However, it is a good idea to indicate the type of the relationship by looking at the covariance between these two values. There seems to be a negative relationship. However, the strength of this relationship can only be observed by correlation, and according to the correlation value, which is negative and close to 1, not very, very, very close to, but significantly close. 0.8 is actually a close value. I mean, it is closer to -1 compared to 0. Therefore, we should say that there is a strong negative relationship between these two variables. As one of them increases, the other one tends to decrease, we can say. So by looking at the correlation value here. There are several descriptive statistics here where we can generate as well. For example, for our data, we can check the histogram of the odometer values, and for 100 automobiles, the odometer values, the distribution of them seems to be similar to normal distribution, but not symmetric enough to say that it is normally distributed. I think it is some other distribution. Okay, the odometer values are distributed with some other distribution. This is not symmetric enough to say that it is normally distributed. However, such distributions will be taught you in the simulation course. For example, this distribution can be a beta distribution. There's a distribution, continuous distribution called beta distribution, and beta the odometer values of this second-hand automobiles can be beta distributed. And another, for the histogram of the second-hand prices, when we look at it, again, a normal distribution is not a good candidate here because it is not symmetric enough for the normal distribution. Again, beta distribution can be a good candidate to distribute such a histogram, to model such a histogram, such a data. Okay, there are other descriptive statistics which you are going to learn in the second semester in the statistics course, such as the box plot diagram. Okay, but I'm not going to teach the theory behind these statistics here. But at this point, let me tell you that it is possible to do everything with R, such as the statistics. There are too many built-in statistical functions, either in the mathematical form or in the graphical representation. So you can use R for descriptive analysis purposes. All right, so that is just going to be the end of our course with this video. So I hope that you can do much more success in the next semester in the statistics course and also in your future courses. Okay, have fun.